This first lecture is sort of general lecture to give you a sense about epidemiology, vague notions of history about epidemiology and epidemics themselves, to sort of situate the framework in which we're going to be operating. So what I'm going to cover here is very briefly epidemiology, what it means, what it is exactly as a discipline, what sort of historical epidemics are known, and then go through some of the characteristics of epidemiology. So to begin with epidemiology, what is it? So I've included here two definitions. There are many, but they all revolve around the same general idea. So epidemiology, if you take the Wikipedia definition, for instance, it's the study and analysis of the distribution, and that includes who, when, and where, the patterns and determinants of health and disease conditions in populations and in defined populations. Okay. Here I've also included a definition by that you can find in the British Medical Journal, and you can see that this other definition says about the same thing. That second definition also emphasizes the aspect of planning and evaluation of strategies to prevent illness, which is going to be an important part of what we are going to be looking at. Okay, and just for perspective, where does the word epidemiology come from? Well, it's derived from the Greek, and it's the study of what is upon the people, and the study of what happens to the people, essentially. Okay. So to begin with, quite quickly, of course, this is really partial, but what can we say about epidemics? What do we know about the history of epidemics? So the first thing that's going to be important to keep in mind is that epidemics themselves, the events of epidemics, they're among the earliest recorded events in history. Okay, you have to see that there are episodes of diseases afflicting humans that are documented in written history for about as far back as written history goes. And I will come back to that later, but for instance, the spatial aspects are very important, and they were described very early on. Okay, but I will address this very specifically in different lectures. Now, when you think about the way diseases happen, you can sort of look at this hierarchy in both time and likelihood space, if you want, that is given in this graph here. So essentially, things go from, in terms of severity, and in the severity and also extent, things go from an outbreak, which is a sudden increase in the number of cases of a disease that happens in a particular time and place. So that's really localized, typically an outbreak. Then there is also what we call an endemic state, which is a constant maintained increase, and not necessarily only increase. Okay, an endemic can also be something that is present, but that's still thinking about geography as being restricted. Then there's an epidemic, and in that case, it's a rapid spread of a disease. And then finally, what we've been experiencing recently, over the past 2 years with COVID, is what is called a pandemic. And a pandemic involves a much broader spatial extent for the spread of the disease. And here, the graph is also showing you, this is something from Wikipedia, I should point out. The graph is also showing you the sort of way you can think about the different levels of spread of an epidemic or a pandemic. So, like the lowest risk, but the highest potential, the most frequent thing, but the least risky of those things is the existence of risk factors. Okay, and these are everywhere. And then upon certain conditions, these risk factors might translate into the spread of an infectious disease locally. So this axis here is showing you how often things happen from very common to very uncommon, and at the same time how severe the whatever event is happening is, from a low severity to high severity. And you can see, okay, there's always existence of risk factors. Then there might be some spreading of the infectious disease, and then this might go towards an outbreak, and we can either go to a situation where the disease becomes endemic or an epidemic state, and at the most unlikely, less frequent, but most impactful, we can go all the way up to a pandemic. So what we're experiencing right now, or experienced in 2009 with the influenza pandemic, are unfrequent events that have major implications. Okay. Now, as I said, epidemics are known and have been known for quite some time. And so here I've taken a table, again from Wikipedia, where I have summarized, I have indicated the first few known epidemics. And you can see, as I was pointing out, that the first instance is more than 3,000 years ago. Okay. Very little is known about this plague. So just a remark, by the way, in early history, most epidemic events were called plagues. Whether they are actually real plagues, that is, epidemics caused by Yersinia pestis, the causative agent of plague, is not usually known, or we often know actually that it is not a plague. But that generic term was used before diseases became better known. So the plague of Megiddo, I'm not sure, dates back to 1350 BCE. The plague of Athens, that I'll come back to because it's a very important plague, in my view at least, happened in about 430 BC, and it involved Greece, Libya, Egypt, Ethiopia. As pointed out, it's probably typhus or typhoid fever or some sort of viral hemorrhagic fever. But it killed these are very rough estimates, of course, for the very early epidemics, but it's estimated that it killed probably 75 to 100,000 people. Other plagues, the first real massive plague is the Antonine plague, which happened in around 160 to 180 in the Common Era, and which might have been smallpox, killed 5 to 10 million people, which at the time was an enormous fraction of the existing population. Okay, there's plagues that happened in China as well. The plague of Cyprian. There's all sorts of plagues that happened, as you see. So those are now bubonic plagues, whereas before they were not, but these are bubonic plagues. And I'm stopping that table at the end of what is called the first plague pandemic. So humanity was traversed by a certain number of plague pandemics, real plague in this case. We'll talk about it more, but this is these events are the most, they're part of what's called the first plague pandemic. Okay, so you can see the impact on the population was already quite high, or sometimes it was low. So it really depends on the spatial extent of the disease in terms of how many places were affected. So that's it. Now, if you remember in the definition of one of the definitions we saw, the Wikipedia definition of epidemiology, we were interested in who, when, and where. So epidemiology, we said then, was the study and analysis of a distribution, who, when, and where. And so how do we qualify this? First of all, I want to spend make just a quick remark. When you get into epidemiology, you will see that the terminology can be a bit heavy. And this is, here are two papers, one of which I collaborated to, and another by Mogadas, who's a colleague in Toronto, and Laskowski, who I'm not sure where he is now. But anyway, these are papers that have tried to make the vocabulary of epidemiology more accessible to us mathematicians, let's say, because coming from mathematics, the vocabulary is quite different. And so I recommend taking a look at this type of paper. There's many of us that do the same thing, but taking a look at this type of paper will help you get a sense of exactly what are the terms, the terminology that is used in the field, not by us mathematicians, but by people who really practice epidemiology. So, who? Well, the epidemiology, typically when you talk about epidemiology, you mean humans. But we also talk about epidemiology in general. So for instance, you would say plant disease epidemiology, although there might be more specific terms that describe this. But epidemiology is sort of normally for humans, but used in a more general context often. We then talk about epizooties when describing a disease that's prevalent or widespread in an animal population. And the same way as we will talk about pandemics, we talk about panzootics to describe a pandemic for animals. And this brings me to a concept that I won't talk about a lot in this course, but that is very important, and that is One Health. The idea of One Health is that when you consider the health of humans, you cannot consider the health of humans in abstraction of the health of animals and even the environment. Everything is linked, as we have seen very much in, for instance, influenza pandemics or the current COVID pandemic. Both of those pandemics involved at one point at least transmission within animal populations. Okay, and there is this type of graphic that you will see from time to time, which sort of summarizes a One Health approach, which says that there are a variety of communicating contexts that influence health, and that involves humans, animals, and the environment in a sort of completely linked relationship. And that's an important concept. As I said, I won't be going too much into this, but you will see that we will see, for instance, models where we have propagation between several species. This is the type of approach that people are more and more interested in now. Now, this, I was talking before about the fact that the terminology is important, and this is the first instance where we see something like this. Now, if you think about, you've heard the terms, but let's make them clear. What's incidence and what's prevalence, which in a way is part of answering the question when. So incidence is the number of new cases in a population generated within a certain time period. Okay. Prevalence is the number of cases of a disease at a single time point in a population. But the distinction is important, and I will come back to this when we come to modeling proper. There is often, with modelers, a misinterpretation of the terms. We write I of t, and sometimes people will call this prevalence, but I of t is not prevalence. It is, it's not incidence, it's prevalence. So although we denoted I, it's the change in I that's the prevalence. Or the incidence, sorry. It's the change in I that is the incidence. So how I increases is the incidence of new cases. But the value of I is the prevalence. It's how much disease there is in the population. And I will, as I said, come back to this. Now, epidemic curves, one of the good things with COVID, I have to say, I mean, don't take this literally, but there is one good aspect, is that we've heard a lot of epidemiology. Everybody has heard a lot of epidemiology in the past little while, more so than we used to. So, for instance, you have all now seen epidemic curves. So what's an epidemic curve? It's used to record the occurrence of new cases as a function of time. So that is typically incidence, okay? Number of new cases per time unit is the incidence. Typically, what you will see is something that is individualized, so bar plots, when there are too many cases, and when the number of cases becomes large, instead of bar plots, oftentimes people will switch to using continuous curves. Let me illustrate this. So this is SARS-CoV-2, number of new cases per day in Hong Kong. And this is showing different status of the cases. So it's not only showing the numbers, the absolute numbers, which is signified by the height of these bars, but also the nature of the cases. So you see sporadic imported, cluster of imported cases, cluster initiated by a local case, initiated by an imported case. And you can distinguish. So this is Hong Kong at a time when there were very few incident cases, and it was easier to say precisely what was happening. And so it was easy to obtain some information not only on the number of incident cases, but also on the nature of the incident cases. Were they cases that were initiated by an imported case, for instance, as in those dark in these brown parts, or for instance, a cluster initiated by a local case, so local generation of cases, as in the lighter let's say yellowish bars here. So this we've seen a lot throughout COVID. I'm not going to spend a long time, but this is an epidemic curve, so to speak, which becomes more like a curve if you start having a lot of cases. So this graph here is the number of COVID-19 cases on the top and deaths at the bottom in Africa during the February to November 2020 period. And you can see that at the top, they've individualized the cases, although it becomes quite difficult to see because these are tens of thousands of cases a day. And you can see also that using a curve is probably more informative than using these bar plots here, because there is a problem of reporting frequency. A lot of jurisdictions during COVID, but in other diseases as well, don't report cases over the weekend, for instance. So usually it's much more informative to use a 7 days moving average, for instance, which smooths out those irregularities in the reporting that are not irregularities in the transmission of cases. It's just an irregularity in the reporting. And so that continuous curve is a much better view of what is happening than this jagged curve that we see if we look at the daily numbers. Okay, but so this and the previous slide show the type of data that you would have. Now, in terms of where, so who, when, where, so for where, again, and I mentioned that earlier, the localization of the cases is important. And so an epidemic is diseases that are visited upon a population, whereas a pandemic, which we will see again, is an epidemic that has spread across a large region. So typically multiple continents or worldwide. An endemic is a disease that resides within a population. It's transmitting at some level during in the population, but it's not going through waves anymore. Okay, and just a remark, we don't say pandemic. We say pandemic with respect to epidemics, but when a disease has become endemic, we just say it's endemic, and we indicate where it is endemic. So it could be endemic worldwide, or it could be endemic in a region. But typically, we don't speak of a pandemic. Now, in terms of where, and again, this is something we'll come back to later, let me point out probably the first good example of a where situation. And let me point out, by the way, the slides here, in order to make the videos, I've chosen a 4/3 view of the slides, whereas when you will see the slides on the website, you will see that they're in full HD format. So I have simply changed the format a little bit. This way the screen appears better when making the videos, and you can see the video on the side, but some pieces are a bit chopped off compared to what I'm seeing on my screen here, and what you will see in the online version of the slides. So to come back to this is probably the first good spatial epidemiology problem. So this is a cholera outbreak that took place in London in 1854, and it was studied by John Snow, who became sort of household name in epidemiology because of that study. So what was happening if there were deaths from cholera during the outbreak in 1854, and Snow had the idea to plot where the deaths were occurring. So this was where the people were living. So it wasn't where the death was occurring, but where the people were living who died from the cholera epidemic. And what he noticed is that there was a big cluster of cases here. And if you look here, that cross here indicates a water pump. So this is not appearing in the slide. It will appear in the slides that you have. There's another legend there on the left. So the crosses here are water pumps. And so Snow realized that this water pump here seemed to be the epicenter of all these deaths that were happening. And he concluded that nearly all deaths had taken place within a short distance of this Broad Street pump. Okay? And this is a major breakthrough in terms of epidemiology. It's really working out that there is a spatial temporal and spatial in particular association to a particular location. And in this case, a pump that was infected. Okay. Talking about spatial temporal aspects, let's take a brief look at pandemic phases. So you will see in this graph here that defining a pandemic, so in this case it was influenza, but I'm almost certain that the same type of framework was used to describe COVID. But the setting was outlined in the case of influenza. So that's prior to the 2009 influenza pandemic. These are the phases that WHO defines in terms of what a pandemic is. So the first two phases are phases that are not very dangerous. So this is the interpandemic period. The lowest possible level is that there is nothing happening. Okay, there's no, and remember I said this is influenza, but you can take it to any other disease of the same spread potential. So there's no animal influenza virus that's circulating that is causing infections in humans. At the second level, there's 6 levels of pandemic phases. Okay, at the second level, there is animal influenza virus circulating in domesticated or wild animals, and there have been a few infections in humans. So at the second level, you have a strain, an influenza strain that you consider to be potentially dangerous. At the third level, you're in pandemic alert. So in this case, you have had sporadic cases or small clusters of disease in people, but there has not been any human-to-human transmission. When you see this abbreviation, it's human-to-human. So there is no human-to-human transmission yet to the level that there can be little outbreaks. So this is phase 3. At phase 4, we now see human-to-human transmission of either an animal or a human-animal influenza virus. And this transmission seems to generate community-level outbreaks. Okay. Phase 5, okay, things are getting really serious. So the virus that you've identified in phase 4 has caused sustained community level of outbreaks. And furthermore, it's not only in one country, it has spread to 2 countries in one WHO region. I'll come back to this. So this is alert phase 5. Things are becoming really bad. And the top level, the worst that things can be is level 6. In level 6, and additionally to what you have in level 5, you now have spread to at least two WHO regions. Okay, so not only is there sustained transmission in at least two countries in one region, there's that sustained transmission in another WHO region. Okay, WHO regions are, they look like this. There's one for the Americas, one for Europe and Russia, essentially, plus part of Asia. There's one for this region here. I don't remember what the names of the regions are. That's why I'm drawing a blank. There's one for India, and here there's one for North Africa, essentially, one for Africa. So if you have sustained transmission in at least two of these regions, you have a pandemic. And just in passing, I'll point out one little weird thing. The Americas are counted as one WHO region. But if you think about it, if you have transmission in both North and South America, this should be considered a pandemic already. Because these are different hemispheres, and a virus like influenza propagating in the summer and the winter, or the winter and the summer, is a very big risk. So this is sort of a weird consequence of geography, that if you had spread in both North and South America, you would not necessarily say that you have a pandemic, whereas you probably should. But that's just like administrative issues. Now, fighting against infections, remember, so if we go back to the BMAG, the British Medical Journal, BMJ, British Medical Journal, definition of epidemic, there was something to do with fighting against infections. So just briefly, the information is planned to used to plan and evaluate strategies to prevent illness and management of patients. So preventing illness essentially takes two forms. So there can be prophylactic measures or vaccination. Prophylactic measures also, I should say, involve non-pharmaceutical interventions, which we've seen a lot during the COVID pandemic. Or the social distancing measures are meant to prevent illness. So they're part of prophylactic measures, okay? But prophylactic measures can also be pharmaceutical. Vaccination is another very important way to prevent infection. I'll come back to that in a second. And then managing illness involves things such as prevention of further spread. So how do you deal, for example, with an outbreak in a hospital and try to minimize the impact of the outbreak? Or what treatment measures are available against the disease? Now, let me say something about immunization, because it's a very important tool in public health. So the first disease for which immunization was known is smallpox. So there's a mention of immunization of some sort in a Chinese book from the 1550s. So this was it was what was called variolation, because it's the name of smallpox, variola. So the method that was used consisted in powdered smallpox scabs that was put in the nose of the healthy people, that induced some mortality, but that mortality was much lower still than what the mortality was if you got smallpox. Then you have safer inoculation at the end of the 1700s, and then Pasteur extended vaccination to chicken cholera and anthrax and human rabies in the 1880s. As I point out there, herd immunity is a concept that actually comes mostly from mathematical epidemiology, and that concept was not understood at the time. So immunization, whether it's variolation or vaccination, was mostly used for the protection of the individual, not as a tool to fight epidemics on the population level. And just because I think it's important just to show, drive the point of the importance of immunization, this is data that I've pulled from the CDC in the USA, and it shows the number of reported cases of measles per year. And the 3 periods that I'm showing in this graph are the pre-vaccination period, and then the early vaccination period, during which only 1 shot of the vaccine was administered, and starting in, I think it was 93 or 87, I can't remember, but anyway, starting at that date, I could count 81, 82, 83, 84, 85, 86, 87, 88, and starting in 88, they started recommending 2 doses of a vaccine, and this is the era in which there are 2 doses of a vaccine. And you can see that and I should point out, the number of deaths from measles is about 100th of these values, but so it used to be about 6,000 in the pre-vaccination era. It's gone down to almost 0 in the US in present days, and that's due to vaccination. Okay, so this was to give a sort of brief overview of epidemiology, what type of problems people are looking at there. Now I'll briefly give you a sort of history again of mathematical epidemiology. So I'll point out that mathematical epidemiology is an old domain. It is not as old as epidemiology itself, but it's been around for a while, as I will show you in a second, but it has become a very important domain only in recent years. So the first, essentially, paper known in epidemiology is from Daniel Bernoulli, part of the famous Bernoulli family of mathematicians. So Daniel Bernoulli wrote this paper in 1760. Et c'est une nouvelle analyse de la mortalité causée par la petite vérole, la petite vérole being smallpox. So he wrote a mathematical model about smallpox inoculation, not vaccination at the time, inoculation, as I was describing before. So this is a mathematical model. I've included, so you can go to the National Library of France and see the scan, or what I've done is I've taken the whole PDF, because it's a PDF which has all the different papers in that volume of the Annals of the Academy of Science, but I've extracted the one from Bernoulli, and if you click here, you can find that thing directly. It's an interesting paper. It's still quite modern, and that's about the first one, I think, that is known. Another important contributor to mathematical epidemiology is Ronald Ross. So at the end of the 1800s, Ross observed malaria parasites in the gut of a mosquito that had been fed several days earlier on a human that was infected by malaria. So doing this, he proved that malaria is transmitted by mosquitoes and by Plasmodium parasite. Okay, so for that he got the Nobel Prize for Medicine, one of the first ones. But what's most important in terms of our domain, mathematical epidemiology, is that he spent the rest of his life, starting essentially from the early 1900s, studying malaria using sometimes mathematical models. and he was a big proponent of using mathematical approaches to try to understand how to curb malaria. Okay. Now, in 1927 came another sort of breakthrough in mathematical epidemiology, and that's with Kermack and McKendrick. So again, Ross was a medical doctor, Kermack and McKendrick are also physicians, and they wrote a series of papers. The one that's been remembered is the 1927 paper, but there's a few others in that series. They're very modern and very important papers. I'll point out later, I'll point it out here, what is remembered as the Kermack and McKendrick model is actually a particular case of a much bigger model that they published in 1927. It's a bit sad because a lot of people forget that they did a lot more than just write this system of three ODEs that we'll come back to. Okay, so I really recommend taking a look at the papers of Kermack and McKendrick. They're really modern in many aspects. Then there was some activity, and I'm not saying there was no activity, but there wasn't much. Okay, the activity that we saw was sporadic, but compared to what's happened in the past 20 years, and more importantly, since the beginning of COVID-19, this is nothing. I mean, a lot of epidemiology, mathematical epidemiology has happened since the beginning of COVID. I don't know how much of the publications in mathematical epidemiology are represented by the publications on COVID-19, but I would guess that they represent probably 80% of what has ever been published about mathematical epidemiology, although it's only been 2 years. There's a lot of important works that happened prior to the 90s. I'll point out one thing that I'll come back to later, the notion of susceptible, exposed, infected, and recovered that is used in most models dates from then. The fact that we are calling E for exposed what should be L for latent is actually an error that dates back to the prior work before the 90s. Okay, I'll come back to it. So the beginning of MathEpi was mostly mathematical. More recently, things have evolved towards using also computational tools. So there was some numerical work in the 80s, but it was mostly simulation of math models, and it wasn't very extensive. I'll point out this one, these two actually, that I think are really, really important. Okay, they deal with the spatial temporal spread, which is what I work on, but I think they're also very important because they're quite early models. In particular, this model of Baroyan and Vrachev that did computer modeling for the spread of influenza over the old USSR, and that's from 71. Okay, so this is quite early work in the spatial temporal spread of diseases. I think it's a very, well, it's seminal work in that sense. This is a work, for instance, that looks at the spread of influenza in France. I mean, there's a lot of works on numerical aspects. There wasn't that many before, there's a lot now. And I should point out that it's got to the point that before, models could be mathematical with some numerics, whereas now there are publications where there is virtually no mathematics, only numerics. And finally, the last point that I want to make is about the use of data in epidemiology and in mathematical epidemiology as well. So use of data has happened all along. The paper that I was mentioning of Bernoulli or the papers of Kermack and McKendrick, they use data. And actually, if you think about it, many developments in statistics have their origin in work studying the prevalence of infection, for example. It not necessarily infectious diseases, it can also be chronic diseases, but a lot of work in stats has its origin in studying diseases. As I point out, it used to be that the data for chronic diseases was much better than for infectious diseases because it's much easier to gather data about someone who has a long-lasting infection than it is for someone who might be infected for 3 days, who you might very well miss. Now, also starting in the 80s, this group from France, but a few other groups as well, started doing near real-time surveillance of infectious diseases. So I'll come back to this, but this is a more modern approach to surveillance, which is surveilling infectious diseases. Now, with SARS-CoV-1, we started to see really a move towards real-time, not near real-time, but real-time monitoring of infectious disease data and real-time dissemination of infectious disease data. And with SARS-CoV-2, so 20 years essentially after SARS-CoV-1, we have progressed to the point that we see data being disseminated and collected not only by governments, but also by citizens. And with COVID-2, we've seen an explosion in the type of data that has been available.